Hello, thanks for clicking. Welcome to another Modulus 2 production. Today we're going to be learning about the derivatives of polar equations. Okay, so in the last video we talked about the polar coordinate system. Now we're going to use that polar coordinate system and those polar coordinates and do calculus with them. All right, so let's get started on this. Okay, and we'll see how it goes. So let's get right into it. Given a polar equation, r is equal to 4 sine 2 theta. So this is an equation that's in polar form. The radius is written in terms of theta. All right. So again, in rectangular form, y is equal to f of x, right? So y is written in terms of x. Okay, so like y equals x squared plus 5. That's an equation that's in rectangular form, right? Y written in terms of x. Here, r is written in terms of theta. All right, that's the difference. So what I want you to find is the derivative of r with respect to theta. So we got to be careful about what we're being asked when theta is equal to pi over 4. Well, this equation is written in terms of r and theta. So I want to find dr d theta. Well, I can actually do that pretty easily. That's like finding dy dx over here. Y is written in terms of x. It's the same thing. So all I have to do is derive this equation, and it'll tell me the answer. So the derivative of r is dr d theta. The derivative of 4 sine 2 theta is 4 cosine 2 theta times 2 with the chain rule, which gives me 8 cosine 2 theta. And then I want to take dr d theta and evaluate it when theta is pi over 4. So that's 8 cosine 2 times pi over 4, which is going to be 8 cosine pi over 2. But the cosine of pi over 2 is 0, right? So dr d theta is 0. Okay? Right? Because this is 8 times 0 there. All right? So that would be dr d theta evaluated at theta equals pi over 4. Okay, so that's as easy as we can make it. All right, so let's make it a little more complicated. Now, given the polar equation, a different one, r is equal to cosine 2 theta, now I want you to find the derivative of x with respect to theta when theta is equal to pi over 3, the derivative of x with respect to theta. I want you to find dx d theta. Okay, but I don't have x in this equation. I have r in this equation. R is what's written in terms of theta, right? So the question is, how would I find dx d theta? Well, we got to use our trusty conversions that we learned. So we learned about conversions. I want to know what the x coordinate is. So I know that cosine theta is equal to x over r. So x is equal to r cosine theta. But I also know that r is equal to cosine 2 theta. So that means x in terms of theta is cosine 2 theta times cosine theta. So now x is written in terms of theta. So I can find the derivative of x with respect to theta with the product rule. So I'll leave the cosine 2 theta there. The derivative of cosine theta is negative sine theta, plus leave cosine theta. The derivative of cosine 2 theta is negative sine 2 theta times 2. And then I can clean this up a little bit, I guess, and I could get negative sine theta cosine 2 theta minus 2 cosine theta times sine 2 theta. And that is the derivative of x with respect to theta. Okay, so again, now you're going to start using your conversions as well, depending on what derivative I'm asking you for. All right. Okay, so now let's consider a polar curve. R is equal to f of theta. So it's some function in terms of theta. I want you to find the slope of the line tangent to the curve. Okay, well, to find the slope of the line tangent to the curve, you have to be in rectangular coordinates, right? The slope of a tangent line is and will always be dy dx. But the problem is I don't know what y is in terms of x. Right now I have r in terms of theta. That's in polar coordinates. I need something in terms of y and x. Well, let's see. Can we convert from polar back to rectangular? Well, we just did that a minute ago. We know cosine theta is equal to x over r. And if we multiply by r on both sides, we get x equals r cosine theta. And then if we have sine theta is equal to y over r, multiply by r on both sides, y is equal to r sine theta. All right. Now, r is equal to f of theta. So in place of x, I can put f of theta. So x is equal to f of theta cosine theta, and y is equal to f of theta sine theta. So now, how does that help me? Well, I'm trying to find dy dx, but now I have x in terms of theta and y in terms of theta. So what I could do is I could do like I did on the previous slide and find dx d theta. I could derive this with respect to theta. And then I could derive y with respect to theta. And then I'd have dy d theta and dx d theta. But that helps me, because if I take dy d theta and divide by dx d theta, I will get dy dx, right? Just like we did when we worked with parametric equations. Dy dt divided by dx dt was dy dx. This is the same thing. It's very similar. Okay, so now all I have to do then is I need to find dy d theta. Well, we can do that. Let's do that over here. So dy d theta, we'll use the product rule. Leave f of theta. The derivative of sine theta is cosine theta, plus leave sine theta, and the derivative of f of theta is f prime theta. And then let's find dx d theta as well. So leave f of theta. The derivative of cosine theta is minus sine theta, plus leave the cosine theta there, and the derivative of f of theta is f prime theta. So dy d theta is f of theta cosine theta plus f prime of theta sine theta over dx d theta is negative f of theta sine theta plus f prime of theta cosine theta. And this would represent the slope of the tangent line to the curve, this equation. Okay, it is complicated, yeah? But it is a representation for dy dx in polar coordinates. All right, so now, let's suppose that r of theta is equal to 1 plus sine theta, and let's find the slope of the tangent line to the curve at theta equals pi over 3. So to find dy dx, that's the slope of the tangent line, I would have to find dy d theta and divide by dx d theta. Okay, so let's try to find y first, I guess. So sine theta is equal to y over r. So that means y is equal to r sine theta. So y would be 1 plus sine theta times sine theta. Okay, I'm going to distribute that. It would give me sine theta plus sine squared theta. All right, so now I'm going to find dy d theta. Shouldn't be too bad. The derivative of sine is cosine, plus derivative of sine theta squared is 2 sine theta times cosine theta. So I could factor out cosine theta. It's in common. A lot of times it's advantageous to do that. And I get cosine theta times 1 plus 2 sine theta. That's dy d theta. All right, now I got to go find dx d theta. Well, I know cosine of theta is x over r. So x is equal to r cosine theta. So then that makes x equal to 1 plus sine theta, that's r, times cosine. If I distribute, I get cosine theta plus sine theta cosine theta. So now let's find dx d theta. We'll move it over a little bit here. We have to use the product rule. Derivative of cosine is negative sine. And then derivative of sine times cosine leaves sine there. The derivative of cosine is negative sine. Plus leave cosine, and the derivative of sine is cosine. So I'll clean this up here. We have negative sine theta minus sine squared theta plus cosine squared theta. Okay, that's the equation to find the slope of the tangent line. Now I want to take dy dx and evaluate it at theta equals pi over 3. All right, so let's do that. So that's going to be cosine of pi over 3, 1 plus 2 sine pi over 3, over negative sine pi over 3, minus sine squared pi over 3, plus cosine squared pi over 3. All right, let's see what we get. So cosine of pi over 3, that's a half. 1 plus 2 sine pi over 3, that's root 3 over 2. And then underneath, sine of pi over 3 is root 3 over 2. Sine squared is root 3 over 2, but squared. Cosine squared is 1/2 squared. All right, let's see if we can clean this up here. We have 1/2 of 1 plus root 3 over negative root 3 over 2 minus 3/4 plus 1/4. Right? So that's 1/2 plus times 1 plus root 3 over, let's see, that's negative 1/2, right? So that's negative root 3 minus 1 over 2, right? So these two join forces to make negative 1/2, and then I already have a common denominator. And now I can flip over the 2, the fraction that's in the denominator, flip it over. It'll knock out, the 2 will knock out the half, and it'll give me, if I have a little bit of room up here left, 1 plus root 3 over negative root 3 minus 1. Now you can rationalize that if you want, or you can just leave it here, and that would be the answer. Okay, that's the slope of the tangent line at theta equals pi over 3. So finding the slope of the tangent line now is a lot more interesting and a lot more work. All right. Okay, so now finally, let's find the second derivative, d squared y over dx squared, for the polar equation r equals f of theta, with dx dt equals 4 sine theta, dy dt is equal to cosine theta. Okay, so let's talk about the second derivative. Well, the second derivative is really the first derivative, its derivative. But again, if we go back and look, the first derivative is written in terms of theta, not in terms of x. So hopefully if you've seen my videos on parametric equations, you're saying to yourself, well, wait a minute. This is like the same thing. We did the same thing when we did parametric equations, except it was in terms of t, right? We wanted to find the derivative with respect to x of dy dx, but we couldn't do that because the only thing we could find was the derivative, in this case, with respect to theta of dy dx. dy dx is in terms of theta right now. Okay, so I need that correction factor. That correction factor was d theta over dx, right? And then the d thetas cancel each other out. It allowed you to slot the dx there in that position. which is really what I want to find. So then we took the d theta dt, or it was dt dx back in parametric equations, and we put it underneath, and we said that we could find the derivative of dy dx and divide by dx dt as a correction factor. Now we're going to divide by dx d theta as the correction factor. Okay, so it is the same derivation that we did back when we looked at the second derivative for parametric equations. So if you want to see a more in-depth explanation, go check out that video. All right. So we can do this. We need to know what dy dx is. Well, dy dx is equal to dy d theta divided by dx d theta. dy dx, or dy d theta, is cosine theta. Dx d theta is 4 sine theta, okay, which we actually could rewrite if we wanted to. Cosine over sine is cotangent. So we could rewrite this as 1/4 cotangent theta, which is kind of convenient because we're going to have to derive this in a minute. So dy dx prime, the derivative of dy dx with respect to theta, derivative of cotangent is minus cosecant squared. So that's going to be negative 1/4 cosecant squared theta over dx dt. Dx dt is 4 sine theta. That's the correction factor. And if you wanted to, you can do a little bit more with this. It's negative 1/4 over 4 is really 1 over 16. And then cosecant is really 1 over sine. So that's really 1 over sine squared times another sine, which is sine cubed. And that is the second derivative of y with respect to x in terms of theta. Okay, so again, it follows the same rationale as you did when we worked with parametric equations. All right, and that's it here for derivatives of polar coordinates. All right, as always, thanks for clicking.